Okay, hello everybody. So for example 2, I already wrote out the example because it is long and I didn't want to have to write it while talking to you guys. So I'm going to read it really quickly and then we'll get to solving it. So it basically says, suppose you are standing on the shore of a circular pond with a radius of 1 mile and you want to get to a point on the shore directly opposite from where you're standing. You plan to swim 2.1 miles per hour from your current position to another point P on the shore, and then walk at 3 miles per hour along the shore to the terminal point. How should you choose P to minimize the total time for the trip? So this is a confusing ass question. So we're going to draw it out and talk about it. So first of all, here's our pond that I drew, and we have our starting point here. Our goal is to get across the lake at this finishing point, and the radius of the lake is 1 mile. So I drew those in. I'm going to highlight the other information and we'll add it in. So we plan to swim 2 miles per hour from where we're currently standing to some point P on the shore, and then we're going to walk 3 miles per hour along the shore to the terminal point. Okay? And it wants us to choose some P. To kind of describe what's happening here, that means our path is going to be us swimming to some point P on the shore and then walking the remainder of the distance. So I guess this person wants, like, I don't know why they're doing this. It wants us to choose the point P that gives us the shortest time for this trip. So I think this is a really dumb problem for several reasons, which I will enumerate here. First of all, how in the heckity heck are you going to know the different angles and the exact distances and all of this if you're swimming? Also, why would you choose the point P to increase your swimming or your time? Why wouldn't you just swim faster or walk faster? I think this is dumb, but they did do the average walking and swimming time for humans, so at least they kind of did their research. All right, so let's set this up. We need to do some geometry, which I will do in green, to figure out our different values. So this angle right here, we're going to call theta, which means that this angle right here is pi minus theta. Okay, and that's going to help us find these different lengths of our blue line. So this length is called the chord length. I think you guys would have learned this in either algebra or trigonometry. Anyway, the chord length can be found by taking 2 times the radius times sine of theta over 2, where theta is that inner angle of the chord. A chord is just a line from one part of a circle to another part of a circle. And then this portion, let's do red. This guy is just an arc length, or a section of the circumference, and that can be found by taking the radius times pi minus theta. Remember, our radius is 1 mile. Okay, so we want to minimize the total time, and we have, I'm not going to do the have, want to know, whatever for this one because I think it's going to get pretty muddled, but we're just going to set up some equations. So we have that the total time, here, let me rewrite that. T sub total is equal to the time it takes us to swim plus the time it takes us to walk. Okay, so we're going to find each of those individually and then create one equation and take derivatives and solve. So the time it takes us to swim is the distance of swimming divided by our rate. So I'll kind of show you guys that. So we know that the distance of swimming is that chord length, so 2 times our radius 1 times the sine of theta over 2. But this right now is just miles, and we want hours, right? So we're going to do a change of units. I don't know if you guys took chemistry, but this is how you change units. We know that we would be swimming at 2 miles for every 1 hour. So we're just multiplying our distance by some form of 1, right? 2 miles equals 1 hour, 1 hour equals 2 miles, so that's just 1. And when we multiply across, we're going to be able to cancel our miles and get units of just an hour. So the time it takes us to swim is going to be our 2's cancel, so we have sine of theta over 2 hours as the time it'll take us to swim. The time it'll take us to walk is the distance of this arc length times the time, or divided by the rate, either way. Okay, so our arc length is going to be r, which is just 1, times pi minus theta. So we have pi minus theta miles, and we are walking those miles at a pace of 3 miles per every 1 hour. And that gives us pi minus theta over 3 hours. So we can rewrite our total time as a function of theta, and that is sine of theta over 2 plus pi minus theta over 3. I'm going to rewrite this one more time as sine of theta over 2 plus pi over 3 minus theta over 3, basically like taking apart this fraction just because it's going to make it easier for us to take our derivative. So now we want to minimize this total time with respect to t, so we just need to take the derivative of t, which is the derivative of sine is cosine of theta over 2, times the chain rule gives us 1 over 2, because the derivative of theta over 2 with respect to theta is 1 over 2, plus 0. Pi over 3 is just a constant, the derivative of a constant is 0, and then minus 1/3, because negative theta over 3 is just negative 1/3 times theta, so that's how we get that negative 1 over 3. And that is our function, our derivative with respect to theta. Now we're going to set that equal to 0. I don't know why I have that 0 there. And solve for theta. I would use Symbolab if I were you guys, or a calculator, because I don't think you can do this in your head. You shouldn't be able to. If you can, I'm very impressed. And you will get theta is approximately equal to 1.68 radians, which is approximately equal to 96 degrees. Okay, so what that's saying up here on our graph is that we should swim to a point P that has a degree of 96. However, we don't know whether that's the fastest time or the slowest time, right? Because this 96 here is a critical value. And we know from last section that a critical value could either be at a maximum or minimum or an inflection point. So we need to determine what it is, and we're going to use that first derivative test where we do this and then plug in our endpoints and our critical values and figure out which one gives us the minimum we're looking for. So we're going to check critical values and endpoints. And here, just to clarify, our endpoints are our starting position and our ending position. If P is at the starting position, then this angle of theta is 0. If P is at the ending position, i.e. if we swim the whole thing, then this theta is pi. We'd be going the full pi, right? Because the full circle is 2 pi, so half of the circle is an angle of pi. So our starting value is 0, and T of 0 is approximately 1.05 hours. Then we plug in our critical value, which was, where was it? 1.68 radians. And that gives us a time of 1.23 hours. And our ending point is at pi radians, which gives us a time, just so you guys know, I'm plugging these values into our original function t up here. So I'm just plugging 0 in for theta, or 1.68 in for theta, and pi in for theta. And if I do that, I guess theta's here as well. If I do that for pi, I get 1 hour. And we're looking for the minimal time. So our minimal time is this t of pi equals 1 hour. So actually the critical value we found earlier gives us the maximum time. So I guess if we want to swim this the slowest, or we want to do this the slowest way, we swim to an angle of 1.68 radians and then walk. And if we want to do it the fastest, we said our angle is pi, so that means the fastest way to do this is just to swim the entire way. Okay, so for the answer, let me be consistent. For the answer, to minimize the time, you should swim the entire way. That is, you should make P your endpoint. And this will yield a time of 1 hour. All right, so that's our second example of optimization problems. I'll see you guys in the next video.